Good morning. In the last lecture, we seen that the fundamental theorem of Galois theory. Okay, what is the statement? Let K be the normal extension of a field F of characteristic 0. Then prove that there is a one-one correspondence between the set of subfield of K, which contains F, and the set of subgroups of GKF. Okay, and we proved that this one-one correspondence between set of subfield of K which contain F and set of subgroups of GK. That is, psi is the function from x to y, where x is the set of subfield of K, which contain F, and y is the set of subgroups of GKF. And also we prove that the dimension over K over T is order of GKT, and the dimension of T over F is index of GKT in GKF. Now we have to show that this second one and third one statement number. If T is the normal extension of F, if and only if GKT is normal subgroup of GKF. Okay, and look at this one. Okay. So in the last lecture we proved that this one, the dimension of T over F is equal to order of GKF divided by order of GKT, that is index of GKT in GKF. Now, step number third, we have to prove that T is the normal extension of F if and only if GKT is a normal subgroup of GKF. Step third, to prove that if T is normal extension of capital F if and only if GKT is a normal subgroup of GKF. Okay. So in step number third, we have to prove this statement by implies and implied method. Okay, look at this one. Consider. First, we'll consider this one. T is the normal extension of F. T is normal extension, okay, of the field F. Now this statement implies and implied. Okay, sigma of T is contained in T for all sigma belongs to GKF. Okay, in the previous lecture we proved this one. Sigma of T is contained in T if T is the normal extension of F for all sigma belongs to GKF. Okay, so what is the meaning of this one? This implies implied. Okay, the sigma of small t which belongs to capital T for all small t belongs to capital T, and for all sigma belongs to GKF. Is it correct?
Yes, sir.
Okay. Now we have to take the automorphism belongs to J belongs to GKT. Okay. So this implies and implied J of. Okay. Now this is the element from T, and suppose J is the automorphism from GKT. Okay. What is the meaning of this one? GKT is set of those automorphisms of K which leaves every element of T is fixed. Okay, now here the sigma of T belongs to capital T, and apply J on sigma of T. Okay, is equal to what? This is the element of T and J belongs to GKT. So this element fixed now. J of sigma T is equal to sigma of T. Wait. Sigma of T. Okay, for all small t belongs to capital T, sigma belongs to GKF. Okay, and J belongs to GKT. Is it correct?
Yes, sir.
Okay, now as capital J belongs to GKT means J is an automorphism. Is an automorphism defined on K which leaves every element of capital T is fixed. Okay, so here this is the reason for above step. Here, as sigma of T belongs to capital T, it is left fixed. Okay, it is left fixed by an automorphism. Okay, J belongs to GKT. Okay, so thus we get J of sigma of T is equal to what? Sigma of T. Okay, J of sigma of T is equal to sigma of T. Now apply sigma inverse on both sides. Okay, sigma is the what? Belongs to GKF. Sigma is an automorphism of K which leaves every element of F is fixed. So has here sigma belongs to GKF and GKF is what? Group with respect to composition. So G inverse must be exist in GKF. So apply, this is implies and implied. So this sigma inverse of J of sigma of T is equal to sigma inverse of sigma of T. Okay, what is the reason? As sigma belongs to GKF, where GKF is what? Is a group. Okay, is a group of all automorphisms. Okay, of capital K relative to F, relative to F. Okay, that means it leaves every element of F is fixed. So that implies what? Sigma inverse exists. Right. As that implies sigma inverse exists. Okay, and is a member of GKF. Is a member of GKF. Okay, so this implies and implies sigma inverse of J of sigma. Okay, composition of T. Look at this one. Sigma inverse J of sigma of T is equal to sigma into sigma inverse is T. Okay, sigma inverse into sigma is identity operator. Now this one is T as it is. So for this is for all small t belongs to capital T, for all sigma belongs to GKF, and for all J belongs to GKT. Okay, what is the meaning of this one? X inverse is equal to what? H, no? So this means H is the normal subgroup of G, na? Okay.
Yes, sir.
So this implies and implied sigma inverse J and sigma belongs to GKT. For all sigma belongs to GKF, and for all J belongs to GKT. Okay. Any doubt?
No, sir.
Okay. So X inverse is equal to H. So, correct. So this implies sigma inverse J sigma belongs to what? GKT, because reason sigma inverse J into sigma is an automorphism which left every element of capital T. Okay, this is the any other element. Okay, for all T belongs to T. That means this is an automorphism. which leaves every element of capital T is fixed. Okay, hence sigma inverse J sigma is a member of what? GKT. Okay, hence sigma inverse J into sigma is a member of GKT. This implies and implied GKT is normal subgroup of GKF. Is it correct? Okay. If suppose G
Yes,
is
sir.
the group, H is the subgroup of G. Okay. If you have to prove that this H is the normal subgroup of G, then we have to show that X, H, or H. Is X capital H. Okay, for all elements of H. X inverse must be belongs to what? H. Okay. So what is the meaning of this one? XH is equal to HX. Then H is the normal subgroup of
HX.
G. Okay, here we prove that this is the member of GKT. Okay, so it's the kind of sigma inverse J sigma belongs to what? GKT. Hence GKT is the normal subgroup of GKF. Okay, any doubt? Okay, take a step मध्ये आपण necessary sufficient दोन
No, sir.
condition prove केले. Okay, implies and implies step मध्ये असल्यामुळे. Now, the step number 4, we have to prove that GTF is isomorphic to GKF upon GKT. Okay, step 4. What is this last statement? If T is the normal extension of F, then GTF is isomorphic to GKF upon quotient group. Okay, this is the quotient group, GKF upon GKT, where GKT is the normal subgroup of GKF. Here we showed. Okay, आताच proof केलेलं आहे आपण. Hence, this quotient group is well defined. म्हणजे तो quotient group तयार होतोय. If this one is normal subgroup of this one, then the quotient group is well defined. Okay, now we have to show that GTF is isomorphic to GKF upon GKT. Okay, step number 4. If capital T, write down given thing. If capital T is normal extension of F, is normal extension of capital F, then to prove that GTF is isomorphic to quotient group GKF divided by GKT. Okay, now this is our field K. This is E, and this one is F. Okay, so as T is normal extension of what? Capital F. Then, by previous theorem, sigma of T is contained in T, for all sigma belongs to GKF. Okay, we proved this one. That is sigma of small t belongs to capital T, for all small t belongs to capital T, and sigma belongs to GKF. Okay, so therefore sigma induces an automorphism sigma star on T. Okay, so therefore this sigma induces. Okay, sigma is an automorphism on what? K, which leaves every element of F is fixed. Now this sigma is induces an automorphism. automorphism sigma star on what? The subfield T of K. Okay, defined by this sigma star of T is equal to sigma of T. Okay, on the subfield T, the sigma star and sigma both are equal. Okay, so this is the sigma star is what? Restriction of sigma. That is sigma is what? Continuation of that sigma star. Okay, now since
Sigma star.
this sigma leaves every element of F fixed, every element of capital F fixed. Okay, then also sigma star is also leaves every element of F is fixed. That implies sigma star belongs to what? GTF. Okay, is it correct? Sigma star is an isomorphism on T. Okay, defined on T. So this sigma star leaves every element of F is fixed. So this belongs to GTF. Okay, any doubt up to here? Okay, wait a minute.
No, sir.
Now, let phi is the function. We have to show that what? Let GTF is isomorphic to GKF upon GKT. So define one function phi. So let this phi is the function from GKF to GTF. Okay, be defined by phi of sigma is equal to sigma star. Okay, what is the input here? Sigma belongs to GK. And what is the output? Sigma star. That sigma star is what? Restriction of sigma on T, which leaves every element of F is fixed. For all sigma belongs to GKF. Okay. Any doubt up to here?
No, sir.
Let phi of, sorry, let sigma 1 and sigma 2, these are the two elements, belongs to GKF. Okay. So this implies phi of sigma 1 into sigma 2 is equal to, by the definition, sigma 1 into sigma 2 star, which is equal to sigma 1 star into sigma 2 star, which is equal to phi of sigma 1 into phi of sigma 2. This implies phi is homomorphism. आता प्रश्न पडला असेल की हा कसा स्टेप कशी आहे. ओके, स्टेप मागच्या थेरला आपण प्रूव्ह केली. Write down exactly. We have sigma 1 into sigma 2 star. Okay, apply on T. We have on the elements of T, sigma 1 star and sigma 1 star and sigma 1 both are equal. So this is the automorphism on T. So which is equal to what? Sigma 1 into sigma 2 of T. But sigma 2 is what? This one, sigma 1 and sigma 2 is automorphism. Okay, this is sigma 1 into sigma 2 of T. Okay, what is sigma 2 of T? On T, capital T of T. This is sigma 2 star
Sigma
of
2 star
T.
of T.
Okay, this is from 1, from equation 1. What is the reason of this one? This one. Sigma 2 of T is equal to sigma 2 star of T. Okay, now this is the element from T. Okay, and sigma 1 on the element of T. कसा apply होईल तो sigma 1 star. Okay, this is sigma 2 star of T. Okay, so let here x is equal to sigma 2 star of t belongs to capital T. Okay, assume this is an element of T. So here we get sigma 1 into sigma 2 star is equal to what? Sigma 1 star into sigma 2 star. Okay. This write down this in the bracket. Okay. So here the what we get? Phi is an homomorphism. Any doubt up here? Now find the kernel of
No, sir.
phi. What is the kernel of phi? Kernel of phi, which is equal to, this is the subset of domain. What is domain? Sorry, sigma. Sigma belongs to GKF.
GK.
Okay, such that phi of sigma is equal to sigma star is the identity of GTF. Okay, suppose sigma star is the identity. तिकडच्या आयडेंटिटीला कोण कोण मॅप होतील ते कर्नल मध्ये येतील. Okay, is it correct?
Yes,
So
sir.
this is equal to sigma belongs to GKF such that phi of sigma is equal to sigma star, where sigma star is identity. Okay, identity maps of T. Okay, of identity map of T, which is equal to sigma belongs to GKF. Okay, sigma belongs to GKF such that what is this one? Sigma star of T is equal to phi into identity map under TA. Okay, for all T belongs to capital T. Right. Okay, because sigma star is an identity map of T, so that means sigma star of T is equal to T for all T belongs to T. Now, which is equal to, this is right. Sigma belongs to GKF. This sigma belongs to GKF such that sigma star and sigma T both are equal on set T or subfield T. Okay, this is sigma star is equal to sigma of T is equal to T for all T belongs to capital T. Okay, sigma is equal to sigma star on T. Okay, so which is equal to sigma belongs to GKF such that sigma leaves every element of T is fixed. Okay, such that this sigma belongs to what? GKT. The set of sigma is an automorphism of K, which leaves every element of T is fixed. Okay, so this is kernel of phi. Kernel of phi is equal to what we get? GKT. Okay, is it correct? Okay, हा the subset है. हा
Yes, sir.
subset है. Okay, सबूत है, normal सबूत है. So असे घ्यायचे की तो ह्याच्यात नाही यायला पाहिजे तो सिग्नल. So kernel of phi is equal to what? GKT. Now, by the fundamental theorem of homomorphism, algebra 1 chapter lecture number 1, fundamental theorem of homomorphism. We have the image of GKF is isomorphic to what? GKF divided by kernel of phi.
Upon kernel of phi.
Okay, every quotient group is isomorphic to every quotient group is isomorphic to image of okay, that implies phi of GKF. This is phi of GKF is isomorphic to, this is GKF. divided by kernel of T is what? G K T. Okay. Now, what we have? Why is the mapping from G K F to what? G E F. Is it correct? Okay. So pi of G
Yes, sir.
K F is what? Subgroup of or subset of G T F. If it is on 2, then pi of GKF is equal to GTF. Okay. This is the subset of GTF. Subset म्हणजे subgroup असतो. Okay, range
Yes,
is
sir.
subgroup. If phi is the mapping from G to G dash, then phi of G is what? Subgroup of G dash. Okay, this is subgroup of GTF. Okay, any doubt up to here? Now look at here. That implies
No, sir.
order of from this one. Okay, from this one, order of phi of G K F. Okay, is equal to what we get? Order of G K F divided by G K T. Okay, question group. That is index of G K T in what? G K F. Okay, which is equal to dimension of T over F. In step number second, we proved this one. But what is T over F? Second step मध्ये prove केलं. हा मागचं विसरते लगेच. Order of GKT. First statement, index of GKT in GKF. This one. Index of GKT in GKF. Dimension of T over F. Okay, we proved this one. So here we get index of GKF in GKN is what? Dimension of T over F. That is nothing but order of GTF. Is it correct? GTF.
Yes, sir.
Okay, now it is given there. What is given there? What is the reason of this one? It is given that
By corollary.
T is normal extension of F. Okay, it is order of phi of GKF. Okay, so okay, order of phi of GKF is equal to what? Order of GTF. Now, GTF is the subgroup of phi of GKF, and order of this one is equal to what? Order of this. So this implies both are equal. Hence, this implies phi of GKF is equal to what? GTF. हा याचा सबग्रुप आहे, पण याची ऑर्डर कशी आहे? इक्वल आहे. H is the subgroup of G, and order of H is equal to order of G. That implies H is equal to G. Okay, so here we get phi of GKF is equal to what? GTF. So the equation 2 becomes, give it as equation number 2. Okay, so putting the equation, putting the value of phi of GTF is here, equation 2. So equation 2 becomes G T F is isomorphic to G A F divided by G A T. Hence the P. Any doubt up here? Okay. So look at
No,
this one
sir.
again. One statement. This is statement of this theorem. Let K be the normal extension of F of field with characteristic 0. Then there is one correspondence between set of subfield of K and the set of subgroup of GK. Also, if T is the any subfield of K which contain F, then order of dimension of K over T is equal to order of GKT. Dimension of T over F, that is degree of T over F is equal to index of GKT in GKF. Second one, if T is the normal extension of F, if and only if GKT is the normal subgroup of GKF. And third one, if T is the normal extension of F, okay, which is given to us, then GTF is isomorphic to GKF upon GKT. Okay, so this is the end of our chapter number 3. Okay, so we will see some examples. Two examples is there. Okay, consider theorem तुमचे संपले. Chapter number 3. Okay, I'll look at the example. Okay, wait a minute. Examples. Number 1. Let capital K be the field. Capital K be the field of complex number. आता आपण जे आपण बघत होतो ए पी हे सगळं फिल्ड आता इन पर्टिक्युलर आता दिलेलं तुम्हाला कॉम्प्लेक्स नंबर कॅरेक्टरिस्टिक ओके के बी द फील्ड ऑफ कॉम्प्लेक्स नंबर and F be the field of real number. F be the field of real number. Show that K is normal extension of F. Okay, that is we have to show that set of complex number is the normal extension of set of real number. Okay, that is the fixed field of GCF is equal to what? F. That is sorry, fixed field of, we have to show that fixed field of GCR is equal to R.
GCR.
Okay, त्यासाठी आधी GCR मला काढावं लागते.
R.
Okay. Proof. We have capital K is equal to set of complex number A plus IB, where A and B belongs to capital R. Okay. Now K is an extension of F. That is set of complex number is what? Is an extension of F. And the element 1 and R forms a basis of K over F. Okay, so what is the degree of K over F? K over F is equal to 2. And
2.
we have from this K is finite extension of F. Since the degree of K over F is finite, so here K is finite extension of capital F. If the degree of K over F is equal to 2, then order of GKF is what? Also must be 2. Okay, जेवढी काही डिग्री असेल तेवढी ऑर्डर असेल कोणाची GKF म्हणजे तेवढेच त्याचे ऑटोमॉर्फिझम असेल. Okay, hence we can define two automorphisms on set of complex number. Okay. Great. Now let us compute GKF. Let us compute GKF. What is GKF? the set of those automorphisms of capital K which leaves every element of capital F fixed. Okay, suppose if sigma is okay, आता आपल्याला दोन आहे कळलं, but we don't know how many elements are there. Okay, in GK. Okay, so here suppose sigma is any automorphism of K that is on the set of complex number. Then what is sigma of I? Bracket square, which is equal to sigma of I into sigma of I. Okay, which is equal to sigma is an automorphism. It is the operation. So this is sigma of I square, which is equal to what? Sigma of minus 1, which is equal to minus 1. Why minus 1? Because minus 1 belongs to F, that is R. And this sigma leaves every element of R is fixed, that is F is fixed. So sigma of minus 1 is equal to minus 1.
Fixed.
Okay. So here this implies sigma of I bracket square is equal to what we get here? Minus 1. So this implies sigma of I is equal to what? Plus or minus square root of minus 1. So this implies sigma of I is equal to what? Plus or minus. Okay.
Plus minus 1.
दोन images. So here let sigma belongs to G, K, F. Okay, if A plus IB is any element of K, it's any element of K with A and B are where small a and small b are real numbers. Okay, then we have sigma of A plus IB, which is equal to sigma of A plus sigma of I into sigma of B. Okay, why? Because sigma is an automorphism belongs to GTF. It gives us the opposition, which is equal to A is belongs to real number. जर हा सिग्मा GTF मधून येत असेल, the element of this
Sigma of A is equal to A.
What is the value? Sigma of I plus or minus I. Sigma of B belongs to real number. So it leaves every element of real number fixed. So this is B. So here we get sigma of A plus IB is equal to A plus or minus IB. A and B belongs to F. Okay, this implies sigma of A is equal to A and sigma of B is equal to B. Thus, if sigma belongs to GKF, then we have sigma of A plus IB is equal to A plus minus IB. Okay, so it can be easily seen that each of the mapping sigma 1 of A plus IB is equal to A plus IB, which is identity mapping, and the sigma 2 of A plus IB it maps to A minus IB is an automorphism of capital A, and sigma 1 being identity mapping. Okay, hence sigma 1 and sigma 2. Hence we get order of GKF now 2. Okay, जे आपण आधी सुरुवातीला सांगितलं की फक्त दोन येतात ते दोन कसे येतात तर असे येतात. Okay, so hence what is the set GKF? GKF is equal to sigma 1 and sigma 2. This implies order of GKF is equal to 2. Since degree of K over F is equal to 2, hence order of GKF is equal to. Okay, example काय करायचं सेटच्या एक्झाम्पलला डायरेक्ट हे विचारतात ऑर्डर ऑफ GKF where K is the set of real number काय देतात कोणते फील्ड. So you have to find the only degree of extension. Okay, फक्त हे फाइंड करा तुम्ही जे काय आन्सर येईल त्याचे तेवढे लिमिट असतात. ओके, हे हा सिम्बॉल दिला की तुम्हाला अवघड वाटतं क्वेश्चन मग दिसायला अवघड दिसतो. ओके, just you have to find the degree of K over F and that is the order of GKF. काही असेल Q2, Q3, Q of 2⁻⁴ काही असेल fields. Okay, so here the order of GKF is 2. Now we have to find the fixed field of GKF. Find fixed field of GKF. Okay, we prove that, we know that fixed field of GKF, F is contained in, always contained in what? Fixed field of GKF. What is the reason? Because every element belongs to GKF must leaves every element of F is fixed. Okay, GKF अशा ऑटोमॅटिझम घ्यायची की F ला फिक्स करते. Hence F must be contained in fixed field of GKF. What is the fixed field of GKF? Write it down, which is equal to A plus IB. Okay, such that sigma A plus IB is equal to A plus IB for all sigma belongs to GKF. Okay, this is the definition of fixed field of GKF. Okay, this belongs to K. This is the element from K. So let alpha belongs to F. Okay, so this implies sigma of alpha is equal to what? Alpha for all sigma belongs to GKF. Okay, so this implies alpha is the element of fixed field of GKF. Okay, what is this one? It's the field of GKF. Okay, so alpha F मध्ये alpha K मध्ये जाते. That's why F is always contained in fixed field of GKF. Is it correct? Prove केला आपण स्टेटमेंट.
Yes, sir.
GKF. Okay, now let's A plus IB is equal to, suppose A plus IB, this is the element from fixed field of GKF. Okay, so this implies sigma A plus IB is equal to what? A plus IB for all sigma belongs to GKF. So this implies sigma 2 of A plus IB for all sigma belongs to GKF. There are two elements in GKF, sigma 1 and sigma 2. Sigma 1 is the identity mapping. Okay, so neglect it. Take sigma 2. Sigma 2 belongs to GKF and apply sigma 2 on A plus IB. What we get? What is sigma of A plus IB? Sorry.
A minus IB.
Sigma 2 of A plus IB. Just sigma 2 जर मला A plus IB चे Okay, for all ला म्हटले ना, जर तुमचा A plus IB जर GKF मध्ये असेल तर हा काय apply this sigma A plus IB is equal to A plus IB for all sigma belongs to GKF. Okay, so this implies for particular apply this sigma 2 of A plus IB is equal to A plus IB. Now what is the image of this one? A minus IB is equal to what? A plus IB. So this implies 2IB. Okay, this is answer. So 2ib is equal to 0. 2 is not equal to 0. I is not equal to 0. Hence, it must be is equal to 0. 2ib. These are the elements of what? Set of complex number. Set of complex number is field. Field means integral domain. Okay, integral domain means without zero divisor. If the product of two elements is zero, one of them must be zero. असं reason आहे त्याचं. Okay. So B must be zero. जर तुमचा A plus IB the fixed field of GK मध्ये असेल तर B must be zero यायला हवा. Thus, fixed field of GK, fixed field of GKF is equal to A plus IB such that B is equal to what? 0, which is equal to A plus IB. Wait a minute. A plus IB such that A belongs to F and B is equal to 0. Now it is clear. So this is equal to A plus I0 such that A belongs to F, which is equal to A such that A belongs to F, which is equal to what? Set of real number. Okay. Hence, K is normal extension of
Normal extension of.
F. That is, C is normal extension of capital R. Okay. Any doubt on this example? Okay. Now we have one more example.
No, sir.
माहिती नाही पण जेवढं होईल तेवढं घेऊया. झालं की हा चॅप्टर संपतोय. मी देतो एक्झाम्पल ते सॉल्व्ह करत घरी. Okay, solve this one for homework. Second one. Let capital F be a field. Capital be a field of rational number. Okay, rational number. And let capital K is equal to F of 2 raised to 1 by 3, where 2 raised to 1 by 3 is a real root of 2. Sorry, real cube root of 2. Show that the only automorphism of capital K is identity automorphism. Okay, identity automorphism is which automorphism? The question is we have to show that GKF contain only one automorphism, which is identity automorphism. And the next question is K is normal extension of capital F. Okay. What we have to show that here? Here K is given F of 2 raised to 1 by 3, where 2 raised to 1 by 3 is what? Real root of 2. And we have to show that there is only one automorphism in GK. And also we have to prove or disprove. Okay, we have to find that whether this K is normal extension of F or not. Okay. सॉल्व करण्याचा प्रयत्न करत नसेल तर त्या नोट्स मध्ये पहा, तरीही नाही समजत असेल तर पुन्हा विचारा सांगेन. ओके, नोट्स आहेत. अजून एक एक्झाम्पल आहे.
Yes, sir.
The third one, let capital K be an extension of the field F. Okay, F. And F is what? Set of rational number. Okay, F is the set of rational number. Show that any automorphism of capital K must leave every element of F. Every element of F, that is field of rational number. ओके, जर तुमचा बेस फील्ड तुमचा रॅशनल नंबर असेल आणि ए हा कोणताही एक्सटेन्शन असेल, सी असेल, क्यू ऑफ 2⁻³ क्यू ऑफ 2⁻, काही कोणताही असेल तो एक्सटेन्शन. Okay, in between R and Q there are infinite extension of Q. Okay, so K is the any extension of field of rational number, then K, the automorphism of K must leave every element of F is fixed. That is, every element of rational number must be fixed. Okay, let sigma be any automorphism of K. Let P is any integer. There are three possibilities, okay, of rational number. एक तो पॉझिटिव्ह इंटिजर, एक तो निगेटिव्ह इंटिजर असायला पाहिजे, किंवा तो एकतर p/2 या फॉर्म मध्ये असायला हवा. ओके, सपोज लेट p is the any integer. Okay, now step number 1, we claim that sigma of p is equal to p. Okay, if p is the integer. Case 1. Case 1. If p is zero element, okay, zero number. So consider sigma of p is equal to sigma of 0 is equal to what? 0, which is equal to p. Okay, so hence for 0 is true. Sigma leaves every element of integer fixed. Now if suppose p is positive, so what we have? P is equal to 1 plus 1 plus up to so on p times. Okay, so that is sigma of p is equal to sigma of 1 plus 1 plus up to p times. Okay, so that is sigma of p is equal to sigma of 1 plus sigma of 1 up to how many times? P times. Again, identity maps to identity. So sigma of 1 is what? Always 1 plus 1 up to how many times? P times, which is equal to what? P. So hence, if sigma is positive integer, sigma of p is equal to p. In the case number 3, if p is negative integer, okay, then say p is equal to minus q, where q is positive.
Positive integer.
Now sigma of p is equal to sigma of minus q, okay, which is equal to sigma of minus 1 plus minus 1 plus how many times? Q times, which is equal to sigma of minus 1 plus sigma of minus 1. Why? Because sigma is an automorphism, which is equal to sigma of minus 1 is minus 1 plus minus 1 plus up to how many times? Q times. Okay, so which is equal to minus q. What is minus q? P. Okay, so sigma of p is equal to p, where p is negative integer also holds. Now step number 2. Okay, in step number 1, We proved that if sigma is an integer. Now, let alpha belongs to F and alpha be any rational number. Alpha be any rational number. Okay, that implies alpha must be equal to m upon n, where m and n are integers and n is not equal to 0. This is the definition of a rational number. Okay, so if sigma is an automorphism of capital K, so we have sigma of alpha is equal to sigma of m upon n, which is equal to sigma of m into n inverse, which is equal to sigma of m into sigma of n inverse, which is equal to sigma of m into sigma of n bracket inverse. By case number 1 and case number 2, these are the integers. Whether this is positive, negative, or 0. But here n is not equal to 0. Okay, that means n, what is the possibilities of n? Maybe positive or maybe negative. So here m into n inverse, which is equal to m upon n. Okay, so that is equal to what? Alpha. So sigma alpha is equal to what? Alpha. Sigma leaves every element of field of rational number is fixed. असं काय ते सांगा, क्यूच्या एलिमेंटला प्रत्येक एलिमेंटला फिक्स राहतो कोणताही सिग्मा असू दे, because set of rational numbers is the smallest field with characteristic 0, smallest infinite field. Okay, why? Because set of rational number is the smallest infinite field having characteristic 0. Okay, so this is the end of our third chapter. Any doubt up here? Okay, so from today we will
No,
see
sir.
the next chapter, finite field and what is the constructible element. Okay, so thank you for attending the lecture. You can leave now and join the next lecture. Thank you. Wait. Attendance bill. Okay, you can leave now. Thank you for attending.